Sorry for looking like the really sick, brawny paper towel guy. Like I lost all my hair, but I'm dressed like him. Uh, I worked all day out in the sun, and evidently I got a bit more sun than I thought because I was getting ready to start class. All of a sudden I got chills, so now I got a heating pad on and sweatpants and a flannel shirt. I can't even remember the last time I wore a flannel shirt. So it's time to get started. So, does anyone have any last minute questions? This could be about anything in the past. Of course, we've finished chapter 8. I set the homeworks. I think I set them really quite a bit later than they should be. But either way, it's okay. I'm not going to move those forward. But I did go ahead and open up chapter 9 homework and chapter 10 homework. You'll see the date for chapter 10 is kind of weird. Like I think I did it for 9/16, which is a week from tomorrow. That may or may not stick, but I'm definitely not going to make it any earlier. Okay, so I just wanted to let y'all know. I wanted y'all to have it available so you could start it, but also I didn't want to overburden you. So, anybody have any questions? I think this. I was looking at the syllabus if I remember correctly. I think our uh, next face-to-face test, as far as I can tell, should be next week. So I'll be opening that up probably at least Monday, but I might even open it up a little earlier. And you'll have from, whatever day I open it till at least Sunday, the next of the following week. So you'll have about 7 day period. But anyways, it'll be there. Oh, I got a question. Yes, yeah. So I never put a deadline on the. I mean, I think I put a due date, but I don't close it. So all the extra credit assignments, you can pretty much do them the whole time, except for the practice test. I don't give credit for taking a practice test after the test has already been taken. So, but yeah, you can do that. Homeworks as well. In fact, if you have a homework assignment that you would like to do, like maybe you're interested in relativity, so you'd like to do the relativity chapter, I can make that available for you whenever you want, and I can even set it to be due by probably the 28th, I think would be the best date for when that would be due by. And that's pretty much going to be the last set of assignments should be due no later than the 28th, I would assume, because July 1 is, I mean, August 1 is the last day of classes, which is like a Friday, so it doesn't matter for us. Anybody else? Thanks for the question, Beth. All right. Well, let's go ahead and get started. So, we're starting chapter 9 today, and that chapter is called Linear Momentum. And you're going to see that basically what Newton really gave us wasn't F equals ma. It wasn't even F equals m dv dt, which is the more advanced version. It's something quite a bit different, and we're going to discuss that today. And in order to do so, we're going to discuss a quantity called momentum. So you've certainly heard momentum before in a sports context or maybe even political context and stuff like that. But the main thing is it is something that seems really hard to change its path. So if something has a lot of momentum in the regular everyday world, then that means they're sort of like a runaway truck and nothing's going to be able to stop them. That being said, obviously, occasionally people actually are do have the momentum and end up losing anyways. But still, so that's sort of an idea of what the momentum we're going to use in the physics world is. And it's actually the only difference is we have to clean it up and make it mathematically precise. For Newtonian physics is what we're doing right now. There actually has to be a correction to that if we talk about relativistic physics or physics where that takes place whenever the objects that you're dealing with are moving comparably to the speed of light or perhaps in strong gravity fields, stuff of that sort. But anyways, the momentum we define as mass times velocity. So you can see if you think about what would be hardest to stop, like if I stood out there in the road and some kid was coming towards me, what would be hardest to stop? And I would say that whatever that is the thing that has high momentum or a lot of momentum. So when you start thinking, well, what about a bicycle with a little girl on it or a little boy, and it's moving at 5 meters per second? Probably. I mean, I know you're not that comfortable with 5 meters per second because I'm not either. But you probably know that's not a big deal to stop that. Similarly, you might say, well, what about instead of a little girl or boy on a bike at 5 meters per second, what about a person driving a small car like a uh, Cooper Mini or something like that? You see, immediately that's a lot more difficult to stop. And that's mainly because the change that occurred there was mass, because I said they're both going to be moving at 5 meters per second. So, yeah, and going from the weight of a little, or the mass of a little girl and her bike to the mass of a Cooper Mini, you see that the momentum of the Cooper Mini is much better for the same speed. Similarly, if you had a Cooper Mini going 5 meters per second and a Cooper Mini going 50 meters per second, I think you conclude that the Cooper Mini going 50 meters per second is pretty much going to smush you. So again, we reach the conclusion that the higher velocity has it, and it turns out that's it. Okay, and it is a vector quantity. Its momentum is equal to mass times velocity. And remember, velocity is a vector quantity. And when you multiply a vector by a scalar, if the scalar is positive, as mass has to be, then you don't change the direction at all. But you increase the magnitude if the number is greater than one, and you decrease the magnitude if the number is less than one. So let's go ahead and get started. I'm going to start by, now that we have, it seems like just about everybody here, I'm going to start by sharing my screen. And we're going to do like I did last time. Actually, I think the last two times since I lost all my files, got so upset about that. Anyways, we're going to go through the book. So it's best if you have your Pearson open. We're going to be discussing specific examples from the book. I will read them in their entirety, but I won't be pulling them up just because of, copyright issues and everything like that. Again, I know it's a little ridiculous. Probably I'm doing something bad copyright wise just by discussing them online, but hopefully, my my subscribership of like 8 people is probably going to keep me out of prison, or at least keep me from getting sued. Gotta hope so. So, anyways, so we're talking in this chapter about linear momentum, and it's basically given by this quantity, p is equal to m times v. So, for instance, a object of 1 kilogram mass moving at 90 meters per second has a momentum of 90 kilogram meters per second. So that's the unit of momentum, obviously. Whoa, I just drew a 5 instead of a square bracket. So the magnitude of the momentum, excuse me, of the uh, units of momentum, or dimensions of momentum, however you want to think about it, are kilograms times meters per second. And again, it is a vector quantity. Now that I've introduced that quantity and given you a little bit of an idea about it, I'll tell you what Newton's second law is. So Newton's second law gives us that the net external force, and remember, I always write this with the summation. A lot more books are doing this nowadays too, but I usually, just to remind everybody that it's not F equals ma, where F is a particular force. It's the sum of all the forces that are actually acting on the object by other objects and other entities or whatever. That total force, or also called total external force, is equal to, before we had m times a, or m times dv dt. Now we're going to have a little different. So the summation of the forces is equal to the instantaneous rate of change of momentum, like that, which can also be written as dp dt. And this is the more correct and more general version of Newton's second law. You can get back the old version by assuming mass is a constant. So if we assume m equals a constant, then summation forces is equal to d by dt of mv is equal to m dv dt, which is just equal to MA as we originally had it. So you can see, yeah, it's a special case, specifically a special case of Newton's second law, when the mass of the object that you're studying does not vary, then mass times acceleration, or mass times dv/dt, is just equal to the sum of the forces. Otherwise, it's the sum of the forces is equal to dp/dt. Anybody have any questions on that? So in this chapter, we're going to be covering basically nine subsections, and the first one is momentum and its relation to force. The second one is conservation of momentum, which is the most important part of most of this chapter until we get to center of mass. 9.3 is collision and impulse. 9.4 is conservation of energy and momentum in collisions. So that gives us another tool in our toolbox in addition to conservation of momentum. We're now going to say, oh, what about if certain types of energy are conserved? Elastic collisions in one dimension, inelastic collisions, and collisions in two and three dimensions. And then we're going to discuss the center of mass, which is our first application of an integral in a more robust way than just integrating a constant and then integrating one half or that constant times time. So finally, the last section is 9.9, and that's center of mass and translational motion. So the section 9.10, that's the rocket equation, and I don't usually cover that. You got to get in the weeds a little bit with that, and most people that are interested in aerospace engineering or something like that, they're going to have a whole course on orbital mechanics. Sorry, just looking at one of my orbital mechanic books. So there's no sense in doing all that. So now that I have this new version of Newton's second law, we're going to try to address some neat things. So one of the things we just saw was that Newton's second law, F equals dp dt, or the net force F is equal to dp dt, is or can be reduced to the normal version of Newton's second law, which is the summation of forces is equal to m dv dt. So we've got that, but there's something else that we can see right now. So for instance, what if the summation of the forces is equal to zero? And that doesn't mean that there aren't any forces necessarily. It means that if there are forces, well, I don't know what to do there. If there are forces, then they sum up to give you zero. So this is the net force on the, and I'll say body slash system is zero. So what if the net force equals zero? Then zero is equal to dp dt. And of course, if the derivative of something's equal to zero, that means the something has to be a constant. So that means p equals a constant. And it's a vector constant, but it's still a constant. So it has a fixed magnitude and direction is what we're saying here. Okay, so what we've just realized is that if the net force acting on a system, and it's better to talk about it in terms of systems because generally speaking, F equals ma can be applied to each little particle making up a big system. And in this case, it's not F equals ma. We're going to be using a new version of Newton's second law, which is the more correct one, and that's the net force is equal to dp dt. So you can do, dp1 over dt plus equals the summation of the forces sub one, meaning all the forces acting on one, and then another one for two, and then another one for three, and then another one for four, and so on and so forth for n particles. Now you can say, wait a second, what about uh, us treating the system as if it's one big object? We can do that. We can pretend that those n objects are sort of combined together in some way to make a whole object, in which case the total momentum is no longer P1 or P2 or P3, it's P1 vector addition plus P2 plus P3 plus P4, so on and so forth. When you do that, you get a whole nother version that you can work out, and your book talks about this, of the net force equaling dp dt. Okay, any questions on that? All right, we've got someone's background noise coming in, just to let y'all know. I think it went away. There it is. Gotcha. Okay, so by treating it as a system as opposed to just a single object, now we can treat things like 40 balls colliding at one time from maybe three or four racks of pool balls thrown onto a table or something like that. But more specifically, you can also handle what a real object would be, which is in some sense a summation of individual atoms. So when we talk about it that way, then we have something P, which I normally write as a capital P when we're talking about a system, whereas I use a lowercase p when I'm talking about a single object. But the system would be P1 plus P2 plus P3 plus dot dot dot. And if you again carry all this out and combine the equations together, you end up getting an exactly equivalent equation for Newton's second law. Only now it's F, the net force on the system, and by the way, that means you actually do not have forces of, object two on object three and object three on object four on object four on object two and so on and so forth. You won't have any of that. But you will have basically the same thing. So then you say the summation of the net of the forces on the system is equal to dp system over dt. So we can treat it all like that. And now, of course, we also have the extra law that says, oh, by the way, if the net force acting on the system, and again, that only includes the forces that other things are applying to the system, if that net force is zero, then the total momentum P is going to be a constant, and that's going to be extremely, extremely valuable for us to solve physics problems. So I'm going to move on unless anybody has any specific questions about that. Your book has nice little bold print areas where it says the rate of change of momentum of an object is equal to the net force applied to it, and they have Newton's second law interpretation where you get F equals ma, and then they also have, of course, conservation of momentum calculation that I just did. So let's look at example 9.1 from your text. And example 9.1 from your text says, let me go ahead and write it over here. So again, hopefully you have your books out, but I'm going to read it to you anyways. It's got a picture of what I think is Roger Federer, if I remember his name correctly. Uh, there's a couple of those guys that look alike to me, so I can get them all mixed up, even though I'm a sort of big tennis fan or was for a long time. So it says example 9.1, and it has a picture of a person serving a tennis ball. It looks like it's at Wimbledon, probably. Yeah, it's definitely Wimbledon or some other grass court in London. It says for a top player, a tennis ball may leave the racket on the serve with a speed of 55 meters per second, which is about 120 miles per hour. If the ball has a mass of 0.060 kilograms and is in contact with the racket for about 4 milliseconds, estimate the average force on the ball. Would this force be large enough to lift a 70 kilogram person? So that's a neat little calculation. We're going to do that. I will remind you, or actually tell you, that only the weakest of the women's side of the of tennis nowadays serves at 120 miles per hour. Everybody's in the 130s, 140s, and the men's side is 155, 160. So at least that's what I recall last time I watched a match. So what we have here is a mass for the tennis ball that's equal to 0.060 kilograms. We have that it's going to be moving, leaving the racket with a final velocity, because we're going to be talking about a change in momentum, which is P final minus P initial. Okay, so change in delta, like we always say in class and in our previous classes, whenever you have that triangle, that always means final minus initial. So if you have triangle P, that means P final minus P initial. If you have triangle R, it's R final minus R initial. In this case, the velocity, which we're all going to treat as one-dimensional, so I don't have to worry about the vectorness of it. And if I really wanted to discuss the vectorness of it, since it's one dimension, positive would be one direction and negative would be the other. But in this case, it is 55 meters per second, and I would suggest, like I said, that you might want to investigate the same problem with maybe 60, 62 meters per second, because that's a more realistic max speed of a tennis serve nowadays. And it also tells us that it's in contact, and I'm going to call that contact time delta t, and you'll see why in a second, but that contact time is 4 milliseconds. So that's our information, and what we'd like to know is estimate the average force. So F average, which by the way, we often write as F with a bar over it, or sometimes we write it in a greater than, less than bracket set. But F average is what we're wanting, and that's a question mark, and we want to compare it to how does F average compare to mg, which is 70 kilograms times 9.80 meters per second. And just so we'll have a number on that, I get 686, which is way too many sig figs, obviously, but that's okay. Well, I shouldn't say way. It's one too many, or possibly two too many, because of 70 could be 70 flat, or it could be 7 point with time sensitive 1. Okay, now that we have that, we're going to make use of Newton's second law. So Newton's second law says the net external force, F, is equal to dp dt. We're talking about a single object being hit right now, and we're also talking about it being in one dimension. So since it's in one dimension, I'm going to drop the vectors, and I'm going to, instead of this being an exact equals of the net force, I'm going to have it approximately equal to the average net force. So I'm going to say F average, which is what we're looking for, is approximately equal to. Now, this is where I'm going to make it approximate. What I'm supposed to do is consider P at time t plus delta t, and then consider T at time t, subtract them, and then divide that by t plus delta t minus t. However, in doing that, I'm supposed to take the limit as the delta t approaches zero, so that's a little bit more complicated. So what we're going to do instead is do a rough approximation of the derivative by calculating delta p over delta t. So that's why we now have to write it as approximately equal to, and that also is a reason why we'd say it's the average net force. In this case, obviously there's a bunch of potential other forces acting on the ball, but the main thing is the big boy, the big force of all of them is the strings hitting the ball. So in that sense, we can sort of ignore all the other forces. So delta P over delta T, as I advised you, whenever you have that delta, that right side up triangle, followed by a variable, that right side up triangle tells you to take that variable, find its final value, and subtract from that final value its initial value. So in this case, we get P final minus P initial, and this is all going to be over delta t, which we could write t final minus t initial, but we actually have, as you saw me write, delta t equals 4 milliseconds. That's a really good idea of roughly what the delta t should be. And the fact that it's a small unit of time, a few milliseconds, that tells us that we're probably getting fairly close to the actual value, even though we're not taking the limit as delta t approaches zero. So in this case, we're going to say the initial velocity was, of course, zero, so the initial momentum was zero, but the final one is what we're going to actually go for. So the final velocity, or the final momentum, is 0.060 kilograms times 55 meters per second minus zero. Again, that would be m times the initial velocity. So the ball could be drifting a little bit into the court as he hits it, or it could be going straight up or straight down, or maybe drifting outwards if the throw was bad or something like that. But we're going to assume that that's essentially negligible. Okay, so that's why I just assume the initial velocity and therefore the initial momentum is zero. And I'm just going to say 4 times 10 to the negative third seconds. And you can see this is going to give us units of kilograms meters per second squared, which is exactly the Newton. I'm going to go ahead and calculate this now. 0.060 times 55. That's 3.3. Now I'm going to divide that by 4 times 10 to the negative third. And of course, that means dividing by 4 and then multiplying by 1,000. So divided by 4 times 10 to the negative 3. And that gives me 825 newtons. And I underlined the 5 because, oh, actually, I should underline the 2 as well because the 4 times 10 to the negative third limited our result to only 1 sig fig. So it's on the order of 800 newtons. So yeah, that's a pretty significant force, and you can see that's quite a bit larger than necessary to lift a 70 kilogram person. So if you wanted to compare that to how big a force it is, that force is obviously large enough to lift a 70 kilogram person. And remember, a kilogram is about 2.2 pounds. So 70 times 2.2 would be about 140, 168, something like that. So, anyways, anybody have any questions on that one? So that's a really rudimentary example of Newton's second law, but it's good because you just got to get started and understand what the variables mean, that sort of stuff. Let's move on to another example. This one's a little bit more abstract. It's kind of neat. It's called example 9.2. And this one has a picture of a person wearing jeans and a red shirt and some tennis shoes spraying off his car. It says, washing a car, momentum, change, and force. So water leaves a hose at a rate of 1.5 kilograms per second with a speed of 20 meters per second and is aimed at the side of a car which stops it. That is, we ignore any splashing back. What is the force exerted by the water on the car? Okay, so that's maybe not obvious what you're going to do, but we'll start off by trying to identify what the figures are. So they gave us, for instance, that water leaves a hose at a rate of 1.5 kilograms per second. The 1.5 kilograms makes me think the variable is an m, and then of course the second makes me think of a variable being t, so it's like a m over t or delta m over delta t, something like that. So that's what I'm going to call that. Delta m over delta t is equal to 1.5 kilograms per second. So that's our delta m over delta t. That's one of the figures they gave us. We also have that the velocity initially, at least, is equal to 20 meters per second, and they only use 2 sig figs, or they only use 2 0, which could be 2 sig figs, or it could be 1 sig fig. Remember, that's one of the potential questions that you've run into on your practice test, specifically in the realm of practice tests and test banks that I've been working with. You're supposed to adhere to the teachings of Giancoli's book. So one of the issues, which I've told you a different version of what 2 0 is, but one of the versions is that this is ambiguous, and that's what Giancoli contends. Okay, and that's certainly a reasonable way of looking at it. If someone tells you 200 meters per second, you don't know if they measured that to the nearest hundreds place, to the nearest tens place, to the nearest ones place, the tenths, the hundredths place, or any of that kind of stuff. And writing 200, you just have to put the 2 zeros unless you're using scientific notation. So it could be 1 sig fig, it could be 2 sig figs, it could be 3 sig fig, it could be even more, except if it's just written as 200. Obviously, once you put a decimal place in there, 200.0, for instance, automatically locks you down at 4, whereas 200 point would knock you down as, or lock you down, excuse me, as 3 sig figs. All right. So with this problem, we're wondering what is the force acting on it? It says, what is the force exerted by the water on the car? I'm going to say F, and I'm going to treat this as an average. So I'm going to go ahead and put a bar on it. Okay. And it says, what is the force exerted by the water on the car? We normally call that the force on the car due to the water, which we indicate by writing CW as subscripts in that order. Okay. Just getting you ready for, again, more of what you're going to see. Now, what we know is Newton's second law, says the net force is equal to dp dt. Now, in this case, you can sort of pretend like we're thinking of individual molecules of water, and then you're actually dealing with the F equals dp dt of a single object. But you could also think of it as we're dealing with a certain amount of water coming out of the hose, and then it's sort of a thing that initially has a cylindrical shape of some length, stuff like that. So you can think about it that way, or you can think about it as a sum of the individual particles and be a little bit more complicated. The main thing is right now we don't have to muddy the waters with that. All we have to do is take F equals delta P delta T, delta P over delta T. So we're going to reduce this complexity by assuming that basically the water will shoot out, let's say horizontally. It's going to hit the side of the car, and as your author suggested, you should expect the water to sort of stick to the car, just run down the side of it, as opposed to taking into consideration that when it hits the actual window or whatever part of the car you're washing, it's going to shoot back. So we're going to assume that it doesn't come back at us at all. So the final velocity is going to be zero. So I'm going to go ahead and write that we say V final is equal to zero, because after arguing that, I think you now understand that's a new piece of information that they sort of hinted at with this problem. So now I'm going to say on average, and what we're saying here, it's not that we're bending the laws of physics and not taking into account all the forces acting on the particular chunk of water or the particles of water. It's that we're trying to actually think of it as an average. So we're going to go F average. I hate it when that happens. F average of CW, which means again the force on the car due to the water is equal to approximately, so I can put that there, that would be delta P over delta T. But remember, this is delta MV over delta T. So you can sort of look at it like that, and you can sort of imagine yourself bringing in the delta M, delta T that way. But and I've seen people solve it this way. I don't necessarily care for it, okay? But you can see that is a potential way. But another way you can think about it, and this is why I kept telling you about thinking of individual particles versus thinking of summing up a bunch of individual particles and then thinking about a chunk of water coming out. If I think about a chunk of water coming out, I can imagine the hose like this, and out comes a column of water. Now it's horizontal, so it might be a little bit apocryphal to call it a column, but either way, you see what's going on. And in fact, if you time that for 1 second, what we'd know is that quantity of water, delta M, would be equal to 1.5 kilograms. So now we can think of that column of water coming, whatever length it would need to be 1.5 kilograms, coming at the actual car and then hitting the car and then laying flat along the car like that. So yeah, believe it or not, that's supposed to be like the car window, and that's the water just running down it. Okay. What we have though is when we do that, we're thinking of the initial velocity being VI equals 20 meters per second, and then V final is equal to 0.0 meters per second. Again, that's by assumption. In fact, we get a slightly bigger quantity if we decided to slightly bigger force if we decided to assume that the water is going to bounce off the window and come back with some velocity. Now, we're talking about the force on the car due to the water, but what I just calculated was delta P, delta T, so I would actually have to calculate that for the actual car itself. But according to Newton's third law, we can say FCW is equal to the negative of FWC, and therefore I can make all this fair game by just putting a negative in front of it. So that's well, actually, I meant to say that before we started, but it slipped my mind, so I wanted to come back and hit it. But basically, what we're looking at now is we're going to find technically what we're going to be finding is the force that the water applies to the car, and now we can use that and Newton's third law to conclude what the force that the car applies to the water is. Or excuse me, yeah, what the force that the water applies to the car is. So with this in mind, we can now say that F CW magnitude, that way I don't have to think about the negative, is equal to, and I'm just going to say change in momentum, which I'm going to, because I want a positive number, I'm going to do the initial first and the final last. So I'm going to say P initial minus P final, just so I can get a positive number divided by delta t. And what we're going to do is, as I wrote in the drawing above, I'm going to treat the delta t as 1 second. So this is going to be basically a initial 1.5 kilograms of water. That's the weight of that column of water, that horizontal column of water. And then its velocity, of course, is 20 meters per second. And then I want to subtract from that, assuming that it's actually zero, of course, uh, as the momentum after. Now, again, as I suggested to you, if we actually assume that the water bounced backwards, then remember that would be now going in the negative direction. So it'd be minus a negative, and minus a negative is the same thing as plus a positive. So we'd end up finding a even bigger force is being exerted on the water by the car, or on the car by the water. But here we go. It was going to be 1.0 seconds, and this should give us the average force in magnitude is equal to 1.5 times 20. Well, 1.5 times 2 is 3, and then 3 times 10 is 30. So this would be 30 meters per second, kilogram meters per second divided by seconds. So this would be 30 newtons is the actual unit of force, is the actual force. Anybody have any questions on that one? Now remember, a newton's about the weight of a quarter pounder before you cook it. So actually, no, it's the weight of a quarter pounder after you melt all the ice off of it. Probably it's a little bit lower, in other words. So it might be even after you cook it and lost some of the grease. The main thing is it's not 0.25; it's like 0.221, so it's a little bit smaller. So this is not a huge force, but you can imagine if you did, like for instance my mom did, which was put a pressure washer tip right on her toe. That broke her toe and cut her open pretty good. But that's a much bigger velocity than this 20 meters per second, and I definitely don't recommend doing that. Anybody have any questions? All right, so that was section 9.2. Now I want to talk about the actual application of conservation of momentum. I've already explained to you how we can see momentum is conserved, and this is an important thing. I want you to realize that when I show you that little derivation, that is a whole physical principle that's a really big deal in physics. Momentum is conserved. That's a big principle, just like charge is conserved. And we used to think mass was conserved. Matter can be neither created nor destroyed. We've since had to correct that a little bit, because we have to say now that mass energy, or matter hyphen energy, can neither be created nor destroyed. The reason why we had to hyphenate it was because, according to Einstein's equation, E equals mc squared, means that every amount of mass corresponds to a amount of energy, and such a way that E is equal to mc squared. So we have to take that into account, but that's obviously a big deal. It's, usually has the word law on it, like conservation law, conservation of charge, conservation of now momentum, and you should know at the drop of a hat under what conditions is momentum conserved. That's exactly why I showed you that little derivation on the previous page. So can someone tell me or type in their chat exactly under what conditions is momentum is conserved? Exactly under what conditions is momentum conserved? So if you look down about three-quarters of the way down that notepad that I pulled up for you, you can see it says, what if the summation of the forces is equal to zero, i.e. the net force on the body slash system is zero? Then zero equals dp dt, which implies P equals a constant. P equals a constant is the definition of conservation of momentum. Okay. So, anyways, momentum is conserved whenever the net external force acting on the system or the object is zero. And when that's the case, then that means momentum is going to be a constant. All right, now that we've gotten through that again, that's just my reminder. So if, for instance, we wanted to study collisions in one dimension, what we might want to look at is something along these lines. So my pen colors are all gone. Okay, so I'm going to start with a little blue ball. Oops, I can make it a little better by making it draw the balls for me. And I'm going to have a little blue ball, and I'm going to have a little red ball, and we're going to assume that those two balls are sort of moving towards each other. Okay. This one has a mass m sub b, and the blue one has a mass of m sub a. Say, okay. And the blue one, of course, has a velocity right now that's VA, and we're just going to call it VA. Okay. You might be tempted to put initial, but your author likes to use just a prime symbol. So if you want to talk about the velocity of A after the collision, it'd be VA prime. So that's why I didn't write that. We notice also I'm drawing here a velocity VB. And notice I didn't say it's negative because it's pointing to the left. So I'm actually allowing the implementation of a VA or a VB being an actual negative number, and that's perfectly acceptable. But I'm treating it as if they're, both positive. So this is before the collision. You can obviously tell because they're headed towards each other. And obviously, if they actually are going to collide, then they're going to then move away from each other. So this should look something along the lines of this and this, and in this case, we're going something like that, pow, pow. And evidently, that was a really bad thing to do with the auto draw on because it just made random shapes that were not cool. So I was trying to say, anyways, that's them actually colliding. And now, after the collision, what we see is put it back on the auto draw is the MA going off to the left. Oops. I just drew that at an angle for no reason. And that is VA prime. And then we also have the red ball, which will be moving the opposite direction, and its velocity will be VB prime, like that. Okay? So when I tell you that P is equal to MV, then that means P, which equals PA plus PB, that has to be equal to MAVA plus MB VB. Similarly, after the collision, P prime is equal to PA prime plus PB prime. And I don't know why I made that P so small, but I did, but that's okay. And this would be MAVA prime plus MB VB prime. And we now have the momentum before the collision, which is just called P, and the momentum after the collision, which is called P prime. And notice I use capitals because it's a system of equations. We have, or a system of particles. In this case, we have two. So if I say the net external force, which I can sometimes write with the subscript ext. So if you see that, like I'm getting ready to do right now, just remember that's what I'm meaning. So the sum of the external forces is equal to zero. If I have that, then the summation forces external oops, left off the E, is equal to dp dt implies 0 is equal to dp dt, which implies P is equal to P final. So I switched back instead of using initials and finals. I switched and started using what your author's using. So I put a prime on the P for the after the collision and a prime, non-prime on the P before the collision. So now I can write that in equation form as M sub A V sub A plus M sub B V sub B is equal to M sub A V sub A prime plus M sub B V sub B prime. This is the equation for conservation of momentum, at least for two particles in one dimension. Actually, it's not even two particles in one dimension. It's two particles in any number of dimensions. I just happen to draw it for one dimension. So I drew everything as moving left or right, but in reality, this could be a three-dimensional problem. And since we wrote it as vectors, that takes that into consideration, and it's still the true version. So whether that's two or three dimensions doesn't matter. So this is conservation of momentum. Momentum for two particles. Anybody have any questions on that? All right, so we're gonna. I'm waiting just in case anybody chats or anything, but we're going to work some other simpler problems, but what I'm wanting to warn you about is I'm going to show you a couple techniques to solve the systems of equations that comes from conservation of momentum. And those techniques are very specific, and I didn't necessarily get it when I was taking this class, so I thought I just had to be really creative like the author was, and the author did exactly the same thing that I'm going to show you today for the calculation. So every time I solve the momentum problem, I didn't use the same idea that the author had showed me. I just kept coming on, flying by the seat of my pants and figuring out my own way. Well, it turns out this is a really difficult thing to solve algebraically, unless you use the way that we're going to show you. So keep that in mind. I'm going to do this for a head-on one-dimensional collision and a head-on one-dimensional elastic collision, which you haven't learned about yet. And then I'm going to do it more generally for a two-dimensional collision. And when I do that, that's another way that's very specific that you need to commit to memory so that you do it every time this way. So keep that in mind. Now we're going to move on and see a simple application of this. So let's consider two railroad cars colliding. So this is example 9.3. And the problem says a 10,000 kilogram railroad car, that's MA, is equal to 10,000 kilogram. Again, this is what Giancoli would call a ambiguous number of sig figs. I'm going to pretend like there's 5 of them. Okay, just to make it easy. So AMA is 10,000 kilogram. It says a 10,000 kilogram car, railroad car A, traveling at a speed of 8 meters per second, strikes an identical car B at rest. If the cars lock together as a result of the collision, what is their common speed just afterward? So I'll read that again in a second, but let me go ahead and write down what we know. I also know that MB, that the other car is identical, so I can assume that its mass is also 10,000 kilograms. I know that the car A, oops, I know that the car A has a velocity A in to the right, basically, which I'm going to call the positive direction of positive 8.0 meters per second. So obviously that writing 8.0 automatically makes that 2 sig figs. And the VB, again, I'm using the symbols that I just introduced. The VB is going to be equal to 0. So the symbols that I just introduced and are in that little red box are the symbols I'm trying to translate this to. And then what we're going to see is VA prime equals VB prime equals question mark. That's really what we're trying to figure out. Now, by writing VA prime equals VB prime, I was taking into account the fact that, well, actually, let me reread the question and see if you can figure out what that was for. So again, reading the question, railroad cars collide, momentum conserved. A 10,000 kilogram railroad car, A, traveling at a speed of 8.0 meters per second, strikes an identical car, B, at rest. If the cars lock together as a result of the collision, what is their common speed just afterward? So, anybody think you have an idea of exactly what I was trying to say with VA prime equals VB prime? Hopefully it's obvious. If it's not, that's okay though. It's a little abstract. All right, well, we're going to move on. It's the fact that they're sticking together means they're going to leave with a common velocity. Okay, this actually is going to turn out to be a totally inelastic collision, which again we'll learn about elastic later. But I just want to introduce that term. So whenever two objects collide and stick together, that's called a completely inelastic collision. So an elastic collision is going to turn out to be one that conserves kinetic energy. So the total kinetic energy, if that's conserved, that type of collision is called a elastic collision. All right, now that we have that, I'm going to use my conservation of momentum that I just derived, and that is MAVA. Notice the pluses and minuses are all we need to indicate the vectorness, so I'm just going to write these as magnitudes. MAVA plus MB is equal to MAVA prime plus MBVB prime, like that. But what we know is, for instance, VB is equal to 0. And what we know also is VA prime is equal to VB prime. So now we can implement that and say, in this case, I'm going to go ahead and put the numbers in, 10,000 kilograms times positive 8.0 meters per second is equal to, now, since I have VA prime equals VB prime, that means I can write this as MA plus MB times V prime, where I'm going to say that's equal to V prime. Okay, just making up a new symbol for that. So I'm going to make use of that and realize, of course, that MA plus MB, since they're identical, is just twice of MA. So this is going to be 20,000 kilograms times this new common velocity V prime. So with that in mind, we find that V prime, which equals VA prime, which also equals VB prime, is in fact equal to 4.0 meters per second, and that's because when you divide both sides by 20,000, you get 10,000 divided by 20,000, that's 1/2 times 8, so that makes it 4. Anybody have any questions on that? Okay, so we'll move on to the next example, and this one is rifle recoil. So if you've ever fired a gun, especially a bigger gun like a rifle or something like that, or a small gun with a lot of punch, you'll see it as well. There's a thing called recoil. And basically what it means is because of conservation of momentum, the gun and the round that's going to be fired, the projectile that's going to shoot out of the gun, you all three are the system. And initially, you're sitting there perfectly still, holding the gun. The gun's sitting perfectly still in your hand, and the bullet sitting, the projectile portion of the bullet is sitting perfectly still within the gun. So the total momentum before the collision, before the actual pulling of the trigger, is 0. Now, what you know is when you pull the trigger that's going to set off an explosion, that explosion is going to force the actual gases up against the projectile. The projectile is going to fire out of the shell and come launching out at some, huge velocity. And the velocity that it leaves will be called the muzzle velocity. The main thing is, since all the forces acting on the system must be zero, then we know momentum is conserved. Now, I said all that, and I offered no claims or specific facts to let you understand that. Hopefully, it came to you anyways. But if it didn't, that's okay. I expected that. But what's going on here is you are holding up the gun, so there is some force of gravity pulling down on the gun. And you are, and actually, to be honest with you, you really don't even have to consider you as part of the system. It could just be the bullet, the actual projectile, and the bullet and the gun itself. I think I might have said that before. I can't remember if I said that and the shooter or what. But the main thing is those three things make up the system, and uh, the forces on the system are you holding the gun. That's got to fight gravity. Well, if it's fighting gravity, then it's not moving up or down. Specifically, it's not accelerating up or down. So the vertical forces add up to give you zero. And additionally, unless you're pushing the gun forward or accelerating it backwards or something like that, there's no real reason to say that the gun is moving initially. So with this conservation of momentum, actually, I just lost where I was going. Uh, so with this, your force acting on the gun, and then the only other force is the gun acting on you. That's part of the internal system, so that doesn't count in F equals ma. The other parts of the explode of the forces are the explosion, a chemical explosion that happens within the shell that basically blows every possible direction, but uh, the barrel is strong enough that the explosion outward, that along with the actual shell casing, is strong enough to keep the explosion inside. The back end is strong enough that it doesn't let the explosion slip out the back end, but the front end has just got a seal between the shell and the actual projectile. And that force is going to act equally, sort of in all those different directions from that explosion. But all those forces are parts of the system acting on other parts of the system. So those forces don't count. Because of that, the net external force on the system is zero. Because of that, we know that momentum is conserved, and therefore we can say the initial momentum, which in this case is just going to be zero, is equal to the final momentum, which in this case is going to be m for the projectile times the muzzle velocity plus m for the actual gun plus the shell technically, but that doesn't matter. It's probably an insignificant amount, times the velocity of the projectile of the gun, and that velocity is what we call recoil velocity, and that's what we're trying to solve for. So hopefully that explanation was sufficient. I know it was quite long, but here we go. Example 9.4. So what we have here is momentum being conserved for something that looks like this. So here's our rifle, something like this. And what we have inside of here is a shell casing and then a projectile inside of the shell casing. Uh, what we're going to say is this is the mass of the bullet. So I'll call that MB. And I'm going to say everything else is the mass of the gun. Okay, now technically, like I said, it's not just the mass of the gun, it's the mass of the gun plus the shell plus any exhaust gas or whatever happens to have been left over after the explosion. But that's, you can tell that's pretty insignificant. And I wrote it as a capital just because it was in such a small space, I ended up making it sharp, but we're going to treat it as a lowercase m. So what's going to happen after the quote unquote collision, which isn't really a collision in this case, is basically the same rifle is going to be moving with a velocity we'll call v recoil. And notice this is not the RC like the force on R due to C. This is RC for the word recoil. And then in addition to that, we're going to have the little projectile, which is the mass mb. And this, of course, has the mass mg. And this one, of course, has a velocity v muzzle. Okay, so I called it muzzle velocity. Your book didn't use that in this particular term, but anyways, I did that. I did choose that way. So the summation forces is equal to zero, as I just argued for quite a long time for you. That tells us that dp, this is a system, so I'm using a capital P, dp over dt is equal to zero, which means p is equal to p prime. And this is all one-dimensional again, so I can just toss the p and the p prime, or excuse me, I can toss the vector symbols and just use p and p prime. So what we have is p is equal to m bullet times 0 plus m gun times 0 is equal to 0, and p prime is m bullet times v muzzle velocity plus m gun times v recoil. Now, what information did they give us? Let me read it again. It says rifle recoil. Calculate the recoil velocity. Actually, I'm thinking I didn't read it to begin with. Sorry about that. So example 9.4, rifle recoil. Calculate the recoil velocity of a 5.0 kilogram rifle that shoots at 0.20 kilogram, shoots a 0.20 kilogram bullet at a speed of 620 meters per second. So let's see what we can figure out here. Uh, what I have is the mass of the gun is 5.0 kilograms, and the mass of the bullet is equal to 0.020 kilograms, and the muzzle velocity, Vm, is equal to 620 meters per second, and the velocity of recoil is what we want to know, and that's the question mark. So now I can say conservation of momentum, oops, implies P is equal to P prime. So what we're going to get is 0 is equal to, oh yeah, that's the bullet first, sorry. I'm trying to write it the same way I had before. And the mass of the bullet is 0.020 kilograms. And the muzzle velocity is 620 meters per second. So we have two sig figs on the mass, but 2 or 3 on the muzzle velocity. Plus, we have the mass of the bullet, which is 0.020. Oops, mass of the rifle now. Sorry about that. This is the 5.0 kilograms times, now in this case, I don't need a parenthesis. I'm just going to write it as V recoil, which is V sub RC. And of course, you can tell it's going to come out negative. And that just says that, hey, you called the muzzle velocity positive 620, and clearly if the actual projectile left to the right at 620 meters per second, which is what I'd call the positive direction, the rifle's going to shoot in the negative direction. So we would expect that to be a negative. And what it is 0.02 times 620. That gives me 12.4, and now I'm going to divide that by 5. And that gives me the answer, which is negative 2.48. And of course, that's one extra sig fig. Oops. That's one extra sig fig. And that is meters per second. And this is the recoil velocity. This is the thing that gives you the sore shoulder the day after a turkey shoot or something like that, or shooting with a shotgun or whatever. Anybody have any questions on that? All right, I'm going to leave conceptual example. Actually, I'm going to read conceptual example 9.5 to you and just get you thinking about it. And I'll leave the answering for later. The book has a good response, so there's no big deal there. But I just want to read it to you so you can think about it. Conceptual example 9.5: falling on or off a sled. An empty sled is sliding on frictionless ice when Jeannie drops vertically from a tree down onto the sled. When she lands, does the sled speed up, slow down, or keep the same speed? So think about that. Jeannie's sitting up in a tree, sled come footing by. All of a sudden, she drops straight down, lands on it, and then the sled and the girl rides away. Did she slow down? Did she speed up? Did she not change at all? Part B. Later, Jeannie falls sideways off the sled. Sled moving this way, Jeannie bloop, falls off to the side. When she drops off, does the sled speed up, slow down, or keep the same speed? So again, those are really good questions to think about. I'll leave it to you, but it's nice for you to start thinking about them a little bit, and hopefully it'll be something that just molds in the back of your head for a little bit of time. Let's get on to another aspect of conservation of momentum, and specifically Newton's second law. So it turns out in Newton's second law, you can play a little bit with the writing of it by saying the summation of the forces is equal to dp dt. If you want to, you can consider multiplying both sides by dt. You get the summation of the forces times dt, keep the vector there, is equal to dp dt. Now that could be a capital P or it could be a lowercase p, because this applies whether it's a system of particles or the same one object or whatever. But now I have this times dt. Now what we can do is integrate both sides. And of course, the right hand side is basically the fundamental theorem of calculus, which says the integral of a derivative is the original function. So that's what we're going to get, but specifically, we're going to get delta p, the change in momentum. So I'm going to say delta p, the change in momentum, which is what this side is. That delta p is equal to the integral of the net force over dt. So in other words, you add up all the forces acting on it and then you integrate it over dt. Now that might make you recall exactly what we learned about the fundamental theorem of calculus and the significance of the integral slash antiderivative versus the derivative. And in this case, actually, I shouldn't be writing that as x and y. I should be really writing it as f and t. So this is the net force on the vertical axis, uh, one dimensional, or the magnitude, you can think of it that way. And this is the time t. And what we have here is maybe some kind of curve that does something like this. And then, of course, that means the area under the curve is this quantity that we're talking about, which is the change in momentum. It is, in fact, actually, I'll switch back to black. It is, in fact, called the impulse. And you see the way we defined it, there's two values of the impulse that you can think of. You can think of the impulse as the integral of the net external force acting on the system over time, or you can think of the impulse as the change in momentum. Both are perfectly acceptable and both are absolutely true because they're obviously equal to each other. When we go to calculate this, the quantity impulse is going to be written as a J with a capital with a vector symbol over it because that's what it is. So this is the defining equation for impulse. So you can see impulse is either the change in momentum, or it's the area under the F versus T curve where F is the net force acting on the system. Either way, that gets it to you, and I wanted to point out exactly what the units of the impulse would be. The units are obviously the units of delta P, which is the units of P, which is kilograms, meters per second. But you could also try to think of this as, let's see, kilogram meters per second. Another way you could think, I'm looking for a, nah, there's not another way that I like necessarily. I was going to introduce in terms of the Newton, but I don't think it comes out very helpful. So we'll just leave it at that. Anybody have any questions? All right, so let me show you how we can use this, and specifically, I'm going to use example 9.6. So here's example 9.6. It says, karate blow. Estimate the impulse and the average force delivered by a karate blow that breaks a board a few centimeters thick. Assume the hand moves at roughly 10 meters per second when it hits the board. So they're asking us to estimate it. We're going to, I would say, assume that the mass of the hand, which this is sort of like the water spraying off the side of the car. Specifically, you're going to take something that has some momentum, the person's hand, and that momentum is going to hit something, specifically the board, and it's going to hit it for a certain period of time. And we can sort of calculate the minimum momentum it must have delivered in the event that the collision took place by having its maximum velocity just as it starts to hit the top surface of the board and reaching a zero velocity as it reaches the bottom of the thickness of the board. So I'm going to write down that the mass of the hand is equal to about 1.0 kilogram. I think that's fairly reasonable. Uh, what we normally do when we're doing estimating, I had Larry Weinstein over at ODU. He wrote the book Guesstimation 2.0 as well, and a couple other books. But he's really big into this making quick back of the envelope calculations, and he's quite good at it. But he tells you in his book that one thing you can do if you're trying to estimate the size of something, like how massive is the hand. I mean, we've never ever, more than likely any of you have ever had a chance to measure a human hand's weight or mass, for obvious reasons. It's connected to a whole arm and stuff like that, so we can't do that. But you can make a reasonable argument, and what Larry Weinstein said was, you can take sort of the one unit, like a 1 kilogram or 10 kilogram or 100 kilogram or 1/10 of a kilogram or 1/100th of a kilogram, and you can sort of make the absolute smallest you could imagine the hand being and the absolute largest you could actually imagine the hand being, and then multiply them and then take the square root of that, because that's called the geometric mean. So if you just take the bottom line, or a bottom estimate of the mass and a top estimate of the mass, and then multiply them and take the square root of that, then that'll give you a good estimate of the mass. And of course, we always, when we're doing estimating, we try to use only one sig fig. So in this case, I just skipped it and said I think the hand's going to be about a kilogram. If I wanted to actually if come up with it, I certainly would not have said the hand is. Yeah, I would have thought the ham was probably right close to a kilogram, so maybe it was a little bit less. So I guess I could say it's on the order of I don't know, 10% of a kilogram is the smallest. No, that's 90% of a kilogram. That's probably what I would say. So zero point 0.9 kilograms would probably be the smallest I'd think it was, maybe zero point 0.8. And then I'd multiply that by, I definitely know a hand's not 22 pounds, which is what 10 kilograms would be. So you could try zero point 0.8, say, and 1, multiply those two, then take the square root. That would be a reasonable example. Or you might say zero point 0.9 and 10. That's going to give you a slightly bigger number, but not hugely bigger. So, anyways, those are some different options. And I highly recommend that book, by the way, Guesstimation 2.0. It's really good. So, anyways, the mass of the hand is going to be about 1 kilogram. We're going to say the velocity of the hand, which they actually gave us an estimate. We're going to say the velocity of the hand, VH initial, is equal to 10 meters per second. Okay, that could be again something where you say, "Well, I definitely know it's 1 meter per second or larger," and then I say, "Well, it's definitely less than 100 meters per second." So maybe we do 1 times 100, and that gives us, of course, 100. And you take the square root of that, and you get, of course, 10. So that would come out exactly right. Now, what are we going to do? Well, we're going to use the idea that the net force, which in this case is just the blow. The karate blow is the big force, and it's monumentally bigger than all the other forces acting on it. So we can sort of say that's really is the only one. Uh, so I'll say F blow, and that's equal to change in momentum over change in time. Now I'm just working with magnitude, so I'm not thinking much about that the two are related through a negative by Newton's third law. I'm just using that. Okay, so we're just jumping straight to it and talks in terms of magnitudes. We're going to say the F below, and I'd say maybe put a bar over it to make it average. Oops, I put an arrow over it to make it a vector. That wasn't right. So F below is approximately equal to the change in momentum of the hand. And what I'm going to say is the change in momentum of the hand is final minus initial. And obviously, final minus initial is going to give me a negative. So I'm just going to do it the other way around, or put absolute value bars around it. So let's say P final minus P initial over delta T. So I'm going to say F below bar is equal to P final, which is going to be 0, absolute value bars, minus P initial. Again, we're assuming the hand's about 1 kilogram. Now, we're also going to assume that the initial velocity is 10 meters per second. So we have that, but how do we do the time? Well, what we can do is use one of our kinematic equations, and our kinematic equation that I'm thinking of is x is equal to v bar t plus x0. Okay. Not only that, I'm thinking of using v bar, if the acceleration is a constant, is v0 plus v1 over 2. So in this case, I'm going to say v bar is going to be 0 meters per second plus 10 meters per second. Divide that by 2. That's going to give me 5.0 meters per second. And then, assuming x0 is equal to 0, I can say t, which is our delta t, is going to be equal to x over v bar. Well, the board is about a centimeter thick, and in fact, the problem tells you that breaks a board a few centimeters thick. So I'm going to call that, two 2 centimeters or 3 centimeters, something like that. So I can go ahead and take for delta t. I'm going to put x over v bar, which is going to be equal to 10 kilograms meters per second divided by, now I'm going to call this 3 centimeters, so that's 3 times 10 to the negative 2 meters divided by 5 meters per second, like that. And that should give me roughly what the force is, 10 kilograms meters per second in the numerator, and 3 times 10 to the negative 2 divided by 5 gives me 0.006. And notice that's meters divided by meters per second, which just gives us seconds. So I'm going to take 10 and divide it by 0.006, and that gives me roughly 1,667 newtons, which we only know to 1 sig fig. So we're going to say roughly 1,000 newtons, something like that. Anybody have any questions on that one? I'm gonna call this 2,000 because it really, if you round it to 1 sig fig, it's got to be 2,000. And that's certainly a fine answer, by the way. Your book, I think, got like actually here it is. your book got 5,000 newtons, but you were talking the same order of magnitude. If it was 10,000, I'd have a problem with it. I'd say that either they estimated too high or I estimated too low. But being within a factor of 10 of each other when you're doing an estimate, that should be fine. So I'm going to say the F below is on the order of 2,000 newtons. So that's one of the ways we can use the impulse equation. Anybody have any questions on that? Well, I've been talking continuously this whole time. It's been an hour and 19 minutes. I think you guys need a break. Let's go ahead and take a break till 7, and I'll come back then. I'm actually going to stay here the whole time, other than maybe stepping away for a second, but I think I'm going to stay here the whole time. So you can ask me questions, but go ahead and take a break. I'm sure you are exhausted. Your brain's probably tired.
How much of it is related to work?
Nothing. Almost
Okay,
zero.
it's
Yeah.
all force. Oh my
Yeah,
god.
this is momentum, which is a whole new quantity, and in fact, we're reverting to go back to a vector quantity.
Wait,
Anyone
what?
else?
Wait, what was? Momentum is a vector.
Momentum is a vector quantity, yes.
Okay, there you go.
Actually, let me check my syllabus. I was mentioning that earlier, and I wanted to check, make sure I was right about what day the face-to-face test is. I'm going to make sure I think I already made the practice test available yesterday, but we'll see. So this week started 7/7. The heck? Oh yeah, face-to-face test 3 due by 7/21. So yeah, it's going to become available ah next week. So you got a whole other week. Online test 5 is due though, so make sure y'all pay attention to that. This is on the recording. I know I gave everybody a break, but just in case anybody hears it, I'll try to remember to say it again. I think we've got about 5 more minutes, 4 more minutes, excuse me. I should have paused this, but when I do, I notoriously forget. 3 more minutes. Two minutes, folks. All right, 1 more minute, folks. Um, Still got about half a minute, but I'm going to share my screen that I'm using on Canvas so y'all can see the syllabus. That way I'll remember not to forget, not to let y'all know what I just told everybody during the break, which was completely unprofessional and gooberlified of me, but here we are. So, all right. So you're now looking at the syllabus page. Just want to point it out to you. So I was actually wrong, or maybe oh well, I forgot what I said. But anyways, 7-7. That's this week that we just started. You can see we're actually a bit behind. That's not a big deal. Ideally, I would like to cover 36, but we very rarely get to. And chapters 14 and 15 we do really really quickly and sort of shortly, so it's not as full breath as you might think. So we can still get this very doable. The main thing is what I'm saying is you do not see any tests necessarily due. I did make online test 5 due, and I think I did not make it 7-7. I think I made it for next week. In other words, I moved the test back, but I'm going to double check that right after I finish here. The main thing I wanted to point out was face-to-face test 3 is going to be due by 7/21. So that's not this week, but the following week that it'll be due. I'm thinking 21. Let's see what day of the week that is. Oh yeah, that's the Monday. So I did. I was afraid I might have written it as Sunday like I normally do, but I did correct it and make sure it was 7/21. So it's basically not this coming Monday, but the Monday thereafter is when that test has to be due. I believe I've already made the practice test. Well, I know I've made the practice test for online test 5 available, but the face-to-face test, we don't necessarily know exactly what chapters are going to be on it yet. But next week, by Monday, I'll put up the actual practice test for that. So that should give you, a week of time with the practice test that's geared towards this particular test. My guess is we'll be through chapters 10 and maybe even 11 by then. So the test will at least include 9 and 10, but it might include 11. Now, I also mentioned about the online test. I wanted to go back and look in the modules and see what I did because I remember doing something Monday. I think I don't know if I sent out a message or I just let y'all see it from the announcements of Canvas, but no, this is online tests for. So I will set this up tonight. In other words, I'm going to go ahead and set the one for 9 and 10. I'll set that up for tonight. And what we're going to do is I'll make this test. You'll see the date when I put it up there, but I'm going to make the online test. I want to make it due not this coming Sunday because I always want you to have a week. So I'll make it due a whole week after I make it available, and I'll make the practice test available. Maybe no, I didn't let that one. Oh, that's why. So I did make practice test 5 available, but it was 5, not online tests 5 that I was talking about. So, anyways, that's what we had there. Anybody have any questions about that schedule? Okay, just pay attention to the dates and also, when you go to the main page of the course, for instance, over here in the right-hand side, there's supposed to be stuff reminding you that it's due. So, I would just advise you to check this at least daily, at least, 5 days during the weekdays, Monday through Friday. So check that, keep an eye on that or whatever. But yeah, I definitely moved to one of the tests. And let's stop sharing and go back to my iPad. So we were talking about momentum, impulse, stuff like that. Now we're going on to show you conservation of momentum and conservation of energy applied to collisions. And when that's applied, we have to assume the collision is elastic, or we have to be told it's elastic. And then we can say kinetic energy is conserved. This is quite often the case at the microscopic level when you're talking about fundamental particles and stuff of that sort, because, the things that normally rob us of kinetic energy are things that require smaller particles than the ones that we're dealing with or something like that. Whereas when you're at the microscopic level, there's pretty much nothing if you ignore quantum mechanics, there's nothing between individual protons or individual electrons or a proton and an electron or a proton and a neutron. So it's really hard to think of ways that kinetic energy be conserved, not be conserved, except for when we start thinking about the attractive forces between them. And if those happen rather quickly, they might not even matter. So anyways, let's go ahead and do share screen. I'm going to go back to my iPad. I'm going back to my iPad. Look, I can't give you better humor than this. This is what physicists have to offer is goofy people like me trying to be funny. All right, conservation of energy and momentum. So we already talked about conservation of momentum, so I want to rewrite that equation. Remember that's MA VA plus MB VB is equal to MA VA prime plus MB VB prime, like that. That is conservation of momentum, whether it be one dimension, two dimension, or even three dimension. The main thing is collision between two particles. Okay. Now, if we talk about conservation of kinetic energy, it's something different. Only conserved in elastic collisions. Whoa, I don't know what happened to the word collisions there. Okay. The conservation of kinetic energy can be stated like this. You'd have 1 half ma VA squared plus 1 half MB VB squared is equal to 1 half MA VA prime squared plus 1 half MB VB prime squared. So you can see we actually get another equation from this. So if we're talking a two-dimensional collision, we're going to have basically that top conservation momentum equation for the x dimension and another one for the y dimension. And then if the kinetic energy is conserved, if it's an elastic collision, then we're going to have a third equation, and that's what we're showing here is all these equations. Now we can also make use of these equations if we go on the assumption that we're dealing with just a simple one-dimensional problem. So that's where we're shooting for next. Now that we have this response or these results that we can use, and by the way, I want to underline this as elastic, and I want to underline this as conservation of linear momentum. And that's only true when the summation forces is equal to zero. Okay, so keep that in mind. Now that we have that, we can actually go ahead and attack the same problem we had before. Only this time we're going to specifically assume, which our drawing had it. If you remember, these little balls that we drew up here, these were all going left and right. Nothing, I was trying specifically to draw it as if it was only going left and right. In principle, they could be going up and down as well as left and right, in which case it'd be a two-dimensional problem. But we're trying to investigate a one-dimensional problem basically, so that you have a vector quantity only in the sense that to the right is positive and to the left is negative, from one person's perspective who draws the axes to their right and the negative one to their left. Sorry about getting so technical there, but anyways, didn't want to speak completely incorrectly. So if we talk about elastic collisions in one dimension, that's what we're going to do now. So let's say elastic collisions in one dimension. Actually, I don't need a hyphen on one dimension, because we're not saying one dimensional, we're saying in one dimension. That means something to me in my head. It might not to you. Sorry about that. Okay, so elastic collisions in one dimension. That's what we're going to address. I'm going to start off by drawing a little ball and another little ball. And this ball is a mass ma, and it's going to be moving with a velocity. Whoa, Nelly. With a velocity of va to the right, but it's actually a vector quantity. So right would be indicating the direction, and this one's going to be mass mb, and its velocity is VB, which I've also drawn to the right. Again, I can just use VA and VB, and if it happens to be going to the left, I'd slip in a negative for VB. Or if A turned out to be going to the left, I'd slip in a negative for VA. Now, after the collision, sometime thereafter, we might have a very different scenario in which MA is now moving with a velocity VA prime, and MB is now moving with a velocity VB prime. So that just gives us the following. And again, by assuming everything's in the positive direction, I just use all positive signs. And if it turns out to be one of them's negative, we just slip in a negative for that component and we'll be good to go. So our equations are MA VA plus MB VB is equal to MA VA prime plus MB VB prime. That's conservation of momentum. And now we can also say, what about conservation of kinetic energy? And conservation of kinetic energy, just like we have written above, is 1 half MA VA squared plus 1 half MB VB squared equals 1 half MA VA prime squared plus 1 half MB VB prime squared. So we'll call this equation 1. We'll call this equation 2. And this one, of course, is conservation of kinetic energy in equation 2, and the other one's conservation of momentum. Now, what we find out is a really good way of dealing with this is if we take equation 1 and get all the MA stuff on one side and all the MB stuff on the other. So 1 gives us MA, and now I'm going to pull the MAVA to the left-hand side, or the MAVA prime to the left-hand side. That's going to become minus MAVA prime, but both of them have a common term of MA, so it's going to be VA minus VA prime. Similarly, and actually, I'm sorry, I didn't write that A in the bottom quite as clear as I would have liked to. And now we're going to do the same thing for the other side, except that's going to be MB over there. So we obviously will have a common factor of MB. And on the right-hand side, the positive one would be VB prime. And then we pull the MB VB to the right-hand side. That'll become negative. So I have MB parentheses VB prime minus VB. So this will be a new equation that I'll call 1 prime. Okay, because we're going to make use of that. Now we're going to take equation 2 and first multiply through by 1 half, or excuse me, by 2. So I'm going to say 2 times that, and I'm going to say times 2 there. Now with equation 2, I'm going to do the same thing and try to get all the MA's stuff on the left side and all the MB stuff on the right side. So you can see again, I'm going to get a common factor of MA, and then it's going to be parentheses VA squared. And then of course, when I bring the MA VA prime to the left-hand side, that's going to be a negative. So VA prime squared. And then the same thing happens on the right-hand side. I'll have a common factor of MB. And then the VB is the actual one that's positive. The VB prime is the one that's positive. So it'll be VB prime squared minus VB squared. And this will be called equation 2 prime. So now that we have those, it might not seem all that helpful, but again, this is where I'm teaching you a very specific way that you can solve a system of, where you can solve a one-dimensional head-on collision. Okay, so this work is something that's really helpful and it gets you in the spirit of sort of understanding how to manipulate these equations because in the next chapter we're going to be using a more complex idea when it's two and three dimensions, which actually we're only going to focus on two dimensions. But this technique is something you need to understand. So pay attention to the derivation. Anybody miss any steps so far? Anybody not understand what we did? Okay, let me make sure my chat's on in case anybody tries to tell me that way. I'll do not see anything. Okay, so now that we have that, we can go ahead and make a further simplification. What I want you to notice is in equation 2 prime, this and this are differences of squares. And the trick to this method is recalling that a difference of squares can be easily factored into a plus b times a minus b. So that's pretty much what we're going to do. And I'm going to go for it right now. So let me show you. 2 prime is going to become MA. Now remember, that was the one that had the VA positive, not the VA prime. So it's going to be VA. Remember, it was VA squared minus VA prime squared, but I'm factoring that out. So it's going to be VA plus VA prime times VA minus VA prime. So that's the difference of squares factorization. And then the right hand side is similar, except remember the right hand side, the prime one was the one that was positive. So this will be VB prime plus VB times VB prime minus VB. So again, that should make the equivalent of equation 2 prime. And in fact, this is equivalent of equation 2 prime. Now I can take and divide this by equation 1 prime, which is MA VA, oops, MA VA minus VA prime equals MB times VB prime minus VB. So if I divide 2 prime by 1 prime, then I end up getting, notice the MA's cancel out, the VA minus VA prime cancels out. So we're going to see this canceling out with that, this canceling out with that. We're also going to see this canceling out with this, and we're also going to see this canceling out. Whoa, 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 not that one. We're going to see this canceling out with this. So now that I have that, I can see that the left-hand side of the division of these two equations is just going to be VA plus VA prime is equal to VB prime plus VB. Now, that might not look all that helpful, but it is really, really, really super helpful. So what I'm going to do now is write it in a slightly better way. I'm going to put all the initial stuff before the collision on the left-hand side and all the final stuff on the right-hand side. So this is going to be VA minus VB is equal to and I think I like to put it with a negative out in front. So actually, I'll just do it first. I'll say VB prime and then minus VA prime like that. And you can see they sort of switch roles. It was A minus B, now it's B minus A on the other side. So you can make that a little more consistent by factoring out a negative on the right hand side. So this is going to be VA minus VB is equal to negative VA prime minus VB prime. So you might not see it. It's a little abstract to think this way, but we now have an expression that basically says the difference in the velocities changes sign. So the difference in the velocity before the collision, whatever that is, if you multiply it by -1, that'll be the difference in the velocities after the collision. So that's a whole new thing we can use, and it's another equation that we can use to solve physics problems all by itself. And in doing so, we were taking into account conservation of momentum and conservation of kinetic energy. So it obviously it's only applicable in elastic collisions, but it's also only applicable when we assume that the net external force on the system is zero or really, really small. Okay. Now let's look at example 9.7. Gotta keep it on time. 719. Okay. So example 9.7, it says equal masses. Billiard ball A of mass M moving with speed VA collides head on with ball B of equal mass. What are the speeds of the two balls after the collision, assuming it is elastic? Assume A, both balls are moving initially VA and VB, and B, ball B is initially at rest. So we've got a couple different problems that we're looking at here. Uh, Basically we're just having A run into B in a head-on collision, and we're trying to figure out what are the speeds of the two balls after the collision if it's elastic. And in the first case, we're taking it as both balls are moving, but in the second case, we're taking it as the B particle is actually sitting still, so it's a target particle, if you will. So what we have here is a mass ma and the initial velocity va. And I'm going to say all this for part A. What we're talking about here is part A, where it is elastic, but both balls are moving initially with VA and VB. So I also have MB, excuse me, and VB before the collision, but we also have MA equals MB equals just plain M. Okay. And what we're wanting to know in part A is what is VA prime and what is VB prime. And then when we do part B, we're going to say, yes, we have MA, yes, we have VA, yes, we have MB, and yes, we're going to have VB, but in this case, the VB is going to be zero. We're still going to have MA equals MB equals just plain M. And again, we want to know VA prime equals question mark and VB prime equals question mark. So does everybody understand that? Let's read over. I'll read the problem again. Equal masses. Billiard ball A of mass M moving with speed VA collides head on with ball B of equal mass. What are the speeds of the two balls after the collision, assuming it is elastic? Assume A, both balls are moving initially VA and VB, and B, ball B is initially at rest so that VB equals zero. So that's what we're trying to solve. And I'm going to do so as follows. Actually, I'm going to change the color. I'm going to go make the solution in black. So for part A, what we have is VA minus VB is equal to negative VA prime minus VB prime. By using this, we automatically know that we're using conservation of momentum and conservation of kinetic energy, elastic collisions, in other words, as well as the net external force being equal to zero. So we can plug this in, and what we're going to see is that VA minus VB is equal to negative VA prime and then plus VB prime. So that's what I'm going to call equation one. And now I can plug that into the conservation of momentum equation, for instance, and use that to figure out something else. So in this case, we did say conservation of momentum. So that's MAVA plus MBVB is equal to MAVA prime plus MBVB prime. Now MA equals MB equals just plain M implies that this, and this all go away, and now we have a new equation 2 that says VA plus VB is equal to VA prime plus VB prime. So if I combine 1 and 2, I can just blindly add them together, for instance. We can see what happens. So 1 plus 2 gives me VA. So I'm adding the left-hand side of 1 to the left-hand side of 2. So that means I'm adding this to this. So VA plus VA is 2VA. Negative VB plus VB is 0. So in this case, I get 2VA for the left-hand side plus 0 for the VB. That's also part of the left-hand side. Now for the right-hand side, I've got negative VA prime plus VA prime, so that's going to give me 0. And then I've got VB prime plus VB prime, so that's going to be plus 2 VB prime. And you can obviously see that that's 2VA equals 2VB prime, which means basically they sort of traded velocities. So we find that VB prime, the final velocity of the second particle, the B particle, is actually exactly equal to the initial velocity of the A particle. So that's one result we found. And now we can plug that back into either equation 1 or equation 2 and figure out exactly what VA prime will be. So let's call this 3, and we'll say plug 3 into, let's plug it into 1. What the heck? When I do that, I'm going to get VA minus VB is equal to negative VA prime. And now I'm going to replace VB prime with just plain VA because that's what 3 is. So instead of plus VB prime, I'm going to say plus VA. Now you can see that you can subtract VA from both sides. And with that, we can see that we get negative VB is equal to negative VA prime, or specifically VA prime is equal to VB. So again, like I said, it's just that they sort of traded velocities. Any questions on that one? I'm looking at theirs. They got VB prime equals VA. That's what I got. They got VA prime equals VB. That's what I got. Now we're going to do part B, where part B has the second particle that is acting as a target, so its initial velocity is 0. So let's continue. Part B, we still have VA minus VB is equal to negative VA prime minus VB prime. That's one of the equations. And since we've already, I'm going to call that 1 again, and since we already dealt with conservation of momentum and used the fact that MA equals MB equals M, that means we have the equation where VA plus VB is equal to VB prime, or VA prime plus VB prime, and that's just from the conservation of momentum. So that gives us VA plus VB is equal to VB A prime plus VB prime. But we can now make use of the fact that VB is equal to 0, and that's equal to 0. So now the equation is going to become 1 prime, and 1 prime is going to be equal to basically VA is equal to negative VA prime plus VB prime. And 2 prime is going to be basically VA is equal to VA prime plus VB prime. Okay, so we can add 1 prime and 2 prime. So add 1 prime and 2 prime. When I do this, the left-hand side is going to become 2VA. The right-hand side, however, is going to be negative VA prime plus VA prime, so that's going to be 0. And then VB prime plus VB prime, so that's going to be plus 2VB prime. So from this, we've learned that VB prime is going to be exactly equal to VA, which, by the way, is the same thing we got on the previous result. I'm going to call that equation 3. Let's call it equation 3 prime. What the heck? Since we already used 3 before. So I'll just call it 3 prime. Now I'm going to plug 3 prime into, let's say, 2 prime. So plug 3 prime into. Now I'm just making up a way to try this. It might not work out so nice. I'm sure it will. But it's, probably your book is telling you to add it in one case and subtract it in the other case. I'm just showing you that that's not necessarily the way that you have to do it. When it's this simple, you can actually do it a bunch of different ways. So plug 3 prime into, let's say, 1 prime. Does that actually work though? Uh, yeah, that works. Okay, so when I have that, I'm now going to have VA is equal to negative VA prime plus VB prime, but VB prime is VA, so I'll put that in there. You can see now that minus VA, in other words, if I subtract VA from both sides, they cancel completely out, and what I get is VA prime is equal to 0. So this is actually what you've probably seen before. They call it Newton's cradle, but basically you can imagine sort of like parallel bars. There's one. And then let's say there's another one right here. Obviously, this one's out in front. Okay. So to make sure you see the three-dimension stuff that I'm trying to get you to see, erase that right there. Now I'm going to attach a little string and a ball and a little string, and then there will be another ball, another string, and another ball, and another string, and another ball, and another string. Okay. And you've probably seen those, like if you lift one ball out, so you take this ball and you pull it out like that, then it falls back in, hits the string, and then exactly one ball pops out. Whereas if you did uh, two balls will pop out on the other side, and so on and so forth. That's exactly what's going on in this case, the conservation of kinetic energy, which notice these balls are really, really rigid, kind of hard. It's kind of ironic, but when you talk about elastic collisions, they're more likely to be elastic if the objects that are colliding are really, really rigid, like they can't bend or anything. You can think about that as well, if they're bending, they're stealing some of the energy of the collision to actually crumple metal and heat it up and stuff like that. So maybe that's a better explanation for you. But the main thing is what we see is if you just do two of them instead of worrying about the balls that Newton's cradle has between the two. So, for instance, I have four balls here. If you just had two total, you lift up the left one, it would come down, slide, and collide with the left-hand side of the right ball. That right ball would then take off with exactly the same velocity or very close to the same velocity that the left ball had, and therefore would reach almost the same height that you dropped the left ball from. So that's what's going on with this type of collision. Anybody have any questions on that? All right. We can get a little fancier. We can do another example where the masses are unequal. So I'm going to give that a try right now. So this is example 9.8. I'm going to write that on a separate page. This is example 9.8. And what example 9.8 says, unequal masses, target at rest. A very common practical situation is for a moving object MA to strike a second object MB, the target, at rest, VB equals zero. Assume the objects have unequal masses and that the collision is elastic and occurs along a line, i.e., it's a head-on collision. A, derive equations for VB prime and VA prime in terms of the initial velocity VA of mass MA and the masses MA and MB. Determine the final velocities for part B. It says determine the final velocities if the moving object MA is much, much more massive than the target particle. And then C, determine the final velocities if the moving object is much, much less massive than the target. Okay, so let's go ahead and write that down. What we have here is A, we want VB prime is question mark. We want VA prime is question mark. What we have is MA. We also have MB. So me writing them down is telling you and the world that we're pretending we know these quantities. There it is. It's MA. Oh, that one too. That one's MB, right? So that's all we mean there. We also know that VB is equal to zero. So we've got that recorded. And now we're just wanting to solve for VB prime and VA prime in terms of in terms of VA. Uh, and that's another quantity we know, VA, and MA and MB. And then part B, consider, in this case, they wanted MA much greater than MB. So this is like a Mack truck hitting a fly. And then in part C, consider MA is much less than MB. Now, in the physics world, the bare minimum when you say much, much less than or much, much greater than is a factor of 10 difference, but I generally do not like it at a factor of 10 difference. I prefer it at a factor of 100 difference because then I feel like it's, 1%, and that seems more reasonable to me. But the main thing is at least 10 times. So let's look at the solution. I'm going to write solution in red this time. Let's start off with MA minus, oops, it's VA minus VB is equal to the negative of VA, whoa, Nelly, is equal to the negative of VA prime minus VB prime. So that's going to be what I call equation one. And in this case, we actually can't just divide out the masses, so I have to have a more complex version of conservation of momentum, and that's going to be this, but I am going to go ahead and make use of VB equals zero. So this is going to be MA VA is equal to MA VA prime plus MB VB prime. In principle, I could go back and state the the conservation kinetic energy equation, but we shouldn't need this because we only have two unknowns. And in fact, in introducing a third equation might actually force it to be an unsolvable situation, or I could just make it where you make a really nasty mathematical error. But anyways, we're going to use this as is. I'm going to go ahead and say VB is actually equal to zero there. I should have said that already before. But let's write that again now. I'm going to say 1 is equal to VA is equal to negative VA prime plus VB prime. Okay, so now I have another version, a newer version of 1 and a version of 2. What I want to do at this point is figure out some way to actually solve this for like a VA or a VB. So I'm going to take 1 and I'm going to just solve that for VA prime because then I can substitute that in and ideally eliminate VA and make it all about VB prime. So if I do that, I get VA prime. And you see when I pull it to the left-hand side, it'll become positive, and that's going to make the VA come to the right-hand side and be negative. So VA prime is going to be equal to VB prime minus VA. And that is the actual expression. I'm going to call this equation 3. And we're going to make use of that now. Now I can go ahead and plug all this in and try to make some sense of it. So I'm going to plug 3 into 2. And if I do that, I get MA VA is equal to MA. Now I'm substituting in place of VA prime, VB prime minus VA. So that's how I actually used 3 to plug into 2. And then, of course, I have the rest of equation 2, which is plus MB VB prime. I'm going to simplify that by getting rid of the parentheses. I'm going to get MAVA is equal to MAVB prime minus MAVA plus MB VB prime. And notice we now only have one unknown, and that is the VB prime. So I'm going to get all those terms with VB on one side and all the other terms on the other. So in this case, I'm going to take this term and this term, which you can see both have VB in it, or VB prime in it. And in fact, they're both positive. So I'm going to say MA plus MB, because notice one of them was being multiplied by MA and the other one was being multiplied by MB. So I'm going to say MA MB times VB prime. Now, doing it this way, I more or less accidentally put the what was on the right hand side now on the left hand side. So I just want to point out I have taken it into account this term and I've taken into account this term. So now I've got to bring the other term to the left hand side. And when I do that, you're going to see that I have a MAVA plus MAVA, which is going to equal 2MA VA. Now we're in a position to solve for VB prime, and it's a nice, neat formula that hopefully looks familiar to you. Specifically, VB prime is equal to 2MA over MA plus MB, and then all of that times just plain VA. Now, what I'm pointing at is this looks like the tension formula for the Atwood machine. So the tension formula for the Atwood machine was 2M1 M2G over M1 plus M2. Just like that. So hopefully that'll be something that can help jog your memory. But this technique, of course, works as well. Now that we've gotten that one, I can go back and use, for instance, VA prime, which we wrote in equation 3 in terms of VB prime and VA. So I'm going to do that. So according to 3, oops, go back to red here. So equation 3 gives us that VA prime is equal to VB prime minus VA. Well, that's equal to, of course, 2MA VA over MA plus MB. So that's the first term. I just replaced VB prime with all that. And I put the VA on top because it's going to make it a little easier. Now I'm going to subtract from that just plain VA. Now, in order to do something useful with this, I'm going to need a common denominator. So therefore, I'm going to multiply top and bottom by, oops, I'm going to use a different color so we can see it, by MA plus MB over MA plus MB. And of course, the reason we can do that is because we're just multiplying by 1 on that particular term, and that multiplication by 1 doesn't change the value. So now I'm going to have VA prime is equal to 2MA VA. Now remember this minus in front of the VA, that has to be distributed with the VA through the two top terms. So I'm going to write all this as if it's over just one denominator. And now I'm going to remember to distribute that negative. So I'm going to say minus MAVA and then minus MBVA. And of course, you can now see, I think I can erase a little bit of this extra fraction bar there. Now you can see some simplifications. I've got 2 MAVA minus MAVA. That's going to be just MAVA minus MBVA. And the whole point of this is hopefully you'll see how much this looks like the Atwood machine as well. So we're going to get MAVA minus MB. VB, or excuse me, VA over MA plus MB, and therefore this is the Atwood machine result I was suggesting. We've got MA minus MB over MA plus MB, and all of that times VA. So remember the Atwood machine, the tension was equal to 2m1 m2. Actually, let me write it the way I normally write it. 2m1 over m1 plus m2 times m2g. And then the Atwood machine had the acceleration was m2 minus m1 over m1 plus m2 and all of that times G. So you can see this does sort of look like the Atwood machine results. So hopefully that will help jog your memory when you're trying to either come up with it or derive it. Anybody have any questions on that one? Now we have to deal with the M much greater than B. So MA much greater than MB. Ooh, we were using red. I should probably stick to that. So for part B, MA much greater than MB. If we look at the VB formula, the VB prime, that's equal to 2MA over MA plus MB, all that times VA. Now, what we can do is we can rewrite this so that we can make use of the fact that MA is so much greater than MB by multiplying by 1 over MA on top and bottom. So this is going to become 2 VA on top, and then on the bottom, multiplying by 1 over MA, that's going to be 1 plus MB over MA like that. And if you take the limit as MA approaches infinity, which is sort of the same thing as making MA much greater than MB, you end up getting just 2VA. So what that means is in the event that the particle that's coming in with a huge velocity versus the target particle, if that uh, particle that's going to collide with the target particle is more massive than the target particle, then the target particle is going to get knocked away at twice the velocity that the initial particle had. This is really bad. For instance, if you're talking about any kind of collisions that would happen on the road, where something with a huge mass hits something with a small mass, you can see that the small mass would leave with twice the velocity that the big mass had. If you do the same thing for VA prime, we found VA prime was MA minus MB over MA plus MB. I'm going to divide by MA top and bottom, so that's going to be 1 minus MB over MA divided by 1 plus MB over MA. And then all that, of course, times VA. But you can see as you take the sort of the limit as MA approaches infinity, both the minus term and the plus term in the bottom, both of those are going to go to 0. So you're going to get VA prime is approximately equal to VA. So we found the target moving off at twice the initial velocity, and we found the impacting particle to basically become unaffected. So, of course, that's exactly what happens when a fly, for instance, hits the windshield of a Mack truck. Now you can do the same thing with part C. And for part C, we said MA is much less than MB. We had VB prime is equal to 2MA over MA plus MB times VA. Let's double check, make sure I'm remembering that correctly. VB prime 2MA over MA plus MB VA. Yes, that's right. Okay, so what I'm going to do again in this case is since MB is going to be the big one, I'm going to multiply both the top and bottom by 1 over MB. So 1 over MB divided by 1 over MB. And when I do that, that's going to give me 2 MA over MB divided by, now when the MA hits 1 over MB, that's going to give me MA over MB, but when it hits the MB one, that's just going to give me plus 1, and then I still have the VA out in front. Again, if I take the limit as MB approaches infinity, that's like, because I've got it set up this way, that's just like saying MB is much, much greater than MA. And of course, what that means is this term is going to go to zero, and as will the top term. So in this case, where MA is much, much greater than MB, then excuse me, MB is much, much greater than MA. In this case, the VB is basically going to approximately have a zero velocity, but the VA prime, which equals, double check my sign, is MA, yeah, MA minus MB over MA plus MB. Oh, almost out of time. Yep, it's just that time. You guys are free to go. I'm going to finish this up real quick, but you are free to go. Make sure you chat me your first and last name and say that you're asynchronous if you're from that class or whatever. But thank you. I'll finish this up and then I'll post the video as soon as I can. Oops. And I'm just going to finish this up real quick. This VA, I'm going to again multiply by 1 over MB over 1 over MB. And then this is going to become, and I can take it as the limit as MA over MB goes to 0. That's another way of looking at it. Instead of saying MB goes to infinity, you can say MB or MB goes to 0. And in this case, we're going to get MA over MB minus 1 over MA over MB plus 1, and all that times VA. And in fact, what we find out is that it's going to be equal to negative VA. So when this target particle is supermassive, you're basically going to bounce off of it with the same speed that you ran into it with, acting as if it's infinitely massive. So, any questions on that? Other than that, you guys are free to go. Thanks for coming, everybody. I'm sorry I kept it an extra minute and a half, but we have essentially finished all the conservation of momentum stuff except for two dimensions, and we haven't finished the center of mass. So we're probably going to spend next time finishing up chapter 9 and maybe jump into 10, but I'm not certain. Thank you again, everyone, for showing up. Thank you for chatting me your name. Thanks, Darius. Got you. You're welcome. You're welcome. Oh, same person. Just moved up. Thanks, Adrian. All right, folks. Well, I'm exhausted. I've had a long day. I'm going to go ahead and go. Looks like everybody's chatting me what they need.
I
Go ahead, Adrian.
did you extend the what is it? The what was it?
You
The
mean the test you missed?
three? Yeah.
No, I didn't because I didn't think I wanted to let you, but I'm going to, but
Okay,
this
yeah,
time I'm going to take off
yeah, because I
points.
was about to say, I
Yeah,
thought I forgot mentioning it,
nah,
but I
it's
don't think
okay.
I would have been able.
I'll do it. Are you asynchronous or are you NO2?
I'm asynchronous,
Okay, you
but I
are
don't think I'm going to
asynchronous.
be able to do it even by the end of the week.
Oh, really?
Because I haven't done chapter six. I've just skipped chapter six.
Okay. I'll send you an email when I get it done. So I'll give you a couple more days and
Uh,
then do it. And like I said, it's better for you not to have a zero. So I'll just do it with the 10 points off for being late. And if anybody else wants to contact me about missing one of those online tests, now's your time. I've actually given a couple chances in the past and people didn't take me up on it. I ended up having to drop a few people because they never took me up on it, never made up for the test. I don't like dropping people, but that's what we're supposed to do. So. Thanks, everybody. Anybody else have anything? Andrea, David, Darius, Adriel. How you doing,
So
Adriel?
I had a question.
Yes.
Um, Although I was hoping I could be the last one here to talk about it.
Oh, I can take you to a private room if you'd like.
Yeah, sure.
Okay. All right. I'm going to open up. Let's make sure I can do that this new way. There it is. There it is. No, no, not there. Let's do a breakout room. Okay. And this is Andrea. I'm going to send you to up. Okay. I'm going to meet you in room one, Andrea.
Okay. Um,
Do you know how to get there?
I'm looking through the options, but I don't think
I'm
I,
not sure I know how either, so that makes two of us. Uh, let me say more, and let's say pause breakout rooms. No, that's not it. Spotlight. There should be like a more button for you guys for your end. Ooh, there's some dots right there. Let's check this.
yeah, I don't see a breakout room option.
Uh, it says you're in room right now. It says you're in room one right now. So let me see. It might just be that you're in room one and I haven't gotten there yet, which is a whole different problem. But
I don't
that
think
might be.
so. We're still on the same screen,
Are we in the
so
same? Yeah, that is right.
yeah.
We're seeing that over there. Oh,
This
open all rooms. That's why. Now I'm going to join room one, and you should be in room one. I'm going to. We just finished question and answer session with one of the students, and now I'm back, and everybody's gone. So have a good day. Bye bye.